Hi, welcome back to my class in Mathematics of Investment. For today, we will take up equivalent rates. Now, when do we say two different interest rates are equivalent? Two interest rates are equivalent if they produce the same accumulated value or the same accumulated amount. Again, two interest rates are said to be equivalent if they produce the same accumulated value or the same accumulated amount. So, to find an interest rate that is equivalent to another interest rate, you separately compute the accumulated value for each interest rate and equate the two accumulated values because if the two rates are equivalent, then their accumulated values are equal. And you solve for the unknown equivalent rate that is equivalent to the given interest rate from the equation you obtain by equating the two accumulated values of the equivalent rates. For our first example, consider the following problem. Find the simple interest rate that is equivalent to 7% compounded monthly. In this problem, two interest rates are involved. We have the unknown simple interest rate that we want to find, and the simple interest rate is equivalent to the given compound interest rate of 7% compounded monthly. You write the given is the compound interest rate, which is denoted by J. The compound interest rate given is 7%. And to convert this to decimal number, you divide 7 by 100 or divide 7% by 100%. But in your calculator, you simply divide 7 by 100 and you get 0.07. And the problem says that 7% is compounded monthly, which means that the interest is computed 12 times in 1 year. Thus, the number of conversion periods in 1 year is 12, denoted by M, the number of conversion periods, or the number of interest computations in 1 year. At compound interest, the accumulated value is given by the following formula. At compound interest rate, the accumulated value can be computed using this formula. Accumulated value is denoted by capital A, and at compound interest rate, it is equal to P, the principal, times quantity 1 plus I to the power N, where N is the interest rate per period. In this example, I is the interest rate per month, computed by dividing J, the interest rate per year, divided by the number of interest computations in 1 year. In this example, the interest rate is 0.07, compounded monthly, M is 12, So we divide J by M, 12. And the exponent N is the total number of interest computations 40 years. And the total number of computations, interest computations 40 years denoted by N is equal to M multiplied by T. In our example, M is 12 because the interest rate given is compounded monthly. N is equal to 12. But you notice in this particular problem, the time T is not given. If the time T is not given, you can assign any value to T. Any number of years would do for as value for T. But the simplest is to assign 1 year to T. And that's what we will do in this problem. Again, if the time T is not given, in problems involving equivalent rates, you assign 1 to T, or let T be equal to 1 year. Thus, if T is equal to 1, N equals M, 12 multiplied by T, 1. And N is equal to 12. Now, accumulated value A is now equal to P. Again, the principal P is not given, but we would leave P as is because later on in our equation from which we will obtain the simple interest rate, the P would cancel out. So let P be as is, multiplied by 1 plus I. I is J over M, 0.07 divided by 12. To the power N, N is 12. For T equals 1 year. And let's call this equation 1. Now the required is to find the simple interest rate equivalent to 7% compounded monthly. And the simple interest rate is denoted by small I. At simple interest rate from our previous lesson, the accumulated value is computed by using this formula. Accumulated value or accumulated amount at simple interest rate denoted by capital A equals P, the principal, times quantity 1 plus IT, where I is the simple interest rate. In this particular problem, I is the simple interest rate equivalent to 7% compounded monthly. And as what we did for the accumulated value at compound interest rate of 7%, we let T equals 1 year. We also let T equals 1 year at for the accumulated value at simple interest rate I. And we would get A equals P multiplied by quantity 1 plus I and T is 1. I multiplied by 1 is I. And we call this equation 2. Because the unknown simple interest rate and the given compound interest rate compounded monthly are equivalent rates, they should produce the same accumulated amounts. Thus, we equate the accumulated value A from equation 1 to the accumulated value from equation 2. The A in equation 1, you equate to the value of A in equation 2. In equation 1, the value of A is P times quantity 1 plus 0.07 divided by 12 to the power 12. Again, the accumulated value from equation 1A is P times quantity 1 plus 0.07 divided by 12 to the power 12. And equate this to the value of accumulated value A from equation 2, which is P times quantity 1 plus I. And you can see that, and it is from this equation that we will solve for I. And you can see from this equation that both sides have P, and we divide both sides by P, the principal. And P divided by P is 1, or P over P will cancel out. And the same way, P over P at the right hand side, P over P is 1, or simply cancel out P. And we have quantity 1 plus 0.07 divided by 12 to the power 12 at the left hand side. And at the right hand side, we are left with 1 plus I. And to finally solve for I, we simply transpose 1 to the left hand side. So I now is equal to this quantity 1 plus 0.07 divided by 12 to the power 12. And we transpose 1 to the left hand side. The sign of 1 is positive. When we transpose it, it becomes minus 1. And we compute this quantity, the difference, and what you will get here is a decimal number, and to convert it to percentage, multiply it by 100% and round it off to 2 decimal places. And we will compute this using our calculator. If you have your calculator, that is a scientific calculator, you can compute this directly from your calculator. We have quantity, open parenthesis, 1 plus 0.07 divide by 12, press close parenthesis, then press the exponent or power to the power 12 and minus 1. And you should get 0.07229. If you would compute this directly in your calculator, quantity 1 plus 0.07 divided by 12 to the power 12 minus 1, you should get 0.0722900800562. And you can see that the answer is a decimal number. And to convert this to percentage, multiply that by 100% and round it off to 2 decimal places. So we multiply this. Do not remove that from your calculator. The answer in your calculator, you multiply by 100. And you should get 7.229 multiplying 0.0722900800562 by 100, we get 7.22900800562. It is now in percent. And we round this up to 2 decimal places. The third digit from the decimal point is to be rounded off. So you count 3 digits from the decimal point. 1, 2, 3. The number to be rounded off is 9. Since 9 is more than 5, we add 1 to the preceding digit, 2. And we get 7.23%. .23% is a simple interest rate, and this simple interest rate of 7.23% is equivalent to the given compound rate of 7% compounded monthly, which means that if you compute the accumulated value of any principal for any time t at simple interest rate of 7.23%, that accumulated value is equal to the accumulated value computed for the same principal and the same time t using 7% compounded monthly, because the simple interest rate of 7.23 and the compound interest rate of 7% compounded monthly are equivalent rates. We now consider the following problem for our example 2. What rate compounded quarterly is equivalent to 4 2/3% compounded semi-annually? In this problem, the unknown interest rate is a compound interest rate that is compounded quarterly. And the given interest rate is also a compound interest rate of 4 2/3%, but it is compounded semi-annually. So for this problem, we would only use the formula for the accumulated value at compound interest rate. We start with the given compound interest rate of 4 2/3%. The given compound interest rate is 4 2/3%, and it is denoted by small letter j. And in using the formula, in substituting this into the formula, we should convert this rate to decimal number. So you divide 2 by 3 and you add 4. And you will get 4.6666667%. It is still percent, and we still have to divide that by 100%. We start with 2 divided by 3. We have 2 divided by 3 is 0.666. It's a non-terminating repeating decimal number where 6 is, the digit 6 is repeated without n. And to this answer we add 4. We get 4.66. 4.6 bar percent. The bar above the digit 6 means that the digit 6 is repeatedly without end. But 4.6 bar percent is still in percent. So we have to divide this by 100%. Or in your calculator, you divide the answer in your calculator. 4.66 is repeated without end. Divide that by 100. And you should get 0.04. 0.046 bar. Again, the bar on above 6 means that the digit 6 is repeated without end. When you enter this in your calculator, you press 6 repeatedly. Do not just enter 0.046. You press 0.04 and then 6 repeatedly. And this interest rate of 4 2/3% is compounded semi-annually, which means that the interest will be computed 2 times a year or twice a year. Thus, the number of interest computations denoted by M is equal to 2. 2 semi-annually means the interest will be computed twice a year or 2 times in a year, and that's every 6 months. Now, the accumulated value at compound interest rate is given by the following formula. Accumulated value at compound interest rate denoted by A is equal to P principal times quantity 1 plus I to the power N, where I is the interest rate per period. In our example, small I is the interest rate per 6 months. And small I is given by J divided by M. Where our J, the compound interest rate, is 0.046 bar. .046 bar divided by M is 2. Now, the exponent and the total number of interest computations for t years is equal to M. The number of interest computations for 1 year multiplied by t years. The total number of interest computations for t years denoted by n is equal to m multiplied by t. But again, in this problem, the time is not given, and as I said earlier, if time t is not given, you let t be equal to 1 year. So we let t equals 1, and we compute n. m multiplied by t, m is 2, and t is 1. 2 multiplied by 1 equals 2. Thus, the exponent n is 2. Now, we write the first equation by substituting I and n into this equation. A equals P multiplied by 1 plus I is 0.046 bar divide by 2 to the power n. N is 2. And let's call this equation 1. For the unknown compound interest rate, we also write the expression for accumulated value at the unknown compound interest rate compounded quarterly. And we will equate the two accumulated values from which we will solve for the unknown compound interest rate. The unknown compound interest rate is denoted by J. But the unknown compound interest rate is compounded quarterly, which means that interest is computed 4 times in 1 year every 3 months. And the number of interest computations per year is denoted by M. For the unknown compound interest rate, compounded quarterly, M is equal to 4. Now we write the accumulated value for this unknown compound interest rate compounded quarterly. The accumulated value at compound interest rate J, compounded quarterly, is computed by using this formula. A equals P principal times quantity 1 plus I to the power N, where I is the interest rate per period in the unknown compound interest rate. Small I is the interest rate per 3 months. And small I is given by J divided by M. We write J as is because it is unknown. Divide by M for the unknown compound interest rate. M is 4 because the unknown interest rate is compounded quarterly. So J divided by M, M is 4. The exponent N is the total number of interest computations for T years. And N is equal to M multiplied by T, where M is the number of interest computations per year multiplied by T years. Again, for this unknown compound interest rate, we take T equals 1 year because the time T is not given. So when T equals 1, N now is equal to M4 multiplied by T1. 4 multiplied by 1 is 4. We now write the accumulated value at the unknown compound interest rate. And that would be our equation 2. A equals P multiplied by quantity 1 plus I is J over 4. To the power N, N is 4. And call that equation 2. Now we equate the value of A in equation 1 to the value of A in equation 2, because that is the condition in the definition of equivalent rates that says two rates are equivalent if they produce the same accumulated values. So the accumulated value at 4 and 2/3% compounded semi-annually given by P times quantity 1 plus 0.046 T to the power N. Our N here is 2. The exponent is 2. To the power N, N is empty. For 2 and 2/3, N is 2, semi-annually, M is 2, and T is 1. So the exponent is 2. And this accumulated value at 4 and 2/3% compounded semi-annually, P, and you take note that there is a bar above 6, which means that 6 is repeated without N. And when you enter this decimal number in your calculator, you press 6 repeatedly. And this accumulated value should be equal to the accumulated value at the unknown compound interest rate equals P times quantity. The accumulated value at the given compound interest rate of 4 and 2/3% compounded semi-annually should be equal to the accumulated value at the unknown compound interest rate compounded quarterly. And it is from this equation that we will solve for J, the unknown compound interest rate. And the first step is to eliminate P. You can see that both sides of the equation have P. So we divide both sides of the equation by P. And P over P from the left hand side is 1. So we simply cancel out P. Similarly, at the right hand side, we have P over P, which is 1. So we simply cancel out P at the right hand side of the equation. And we are left with this equation after eliminating P from both sides. But J here is inside the quantity raised to the exponent 4. Thus, to have J at one side of the equation only, we must eliminate the exponent 4. And to do that, we take the natural logarithm of both sides and we apply one property of natural logarithm. We take the ln of the left hand side and we also take the ln or natural logarithm of the right hand side. For the left hand side of the equation, we can calculate the ln of quantity 1 plus 0.046666 without n over 2 to the power 2 because there is no variable at the left hand side. To the right hand side, we apply property of logarithm, natural logarithm, to bring this exponent 4 as coefficient of ln. In particular, we use this property of ln. This property of natural logarithm says that ln of x to the n is equal to n multiplied by ln of x. The exponent n of x becomes the coefficient of ln x. And we apply this property of natural logarithm to the right hand side of the equation, and 4 becomes a coefficient of ln of 1 plus j over 4. We apply this property of natural logarithm to the right hand side of this equation, and the exponent for here becomes the coefficient of ln. For the right hand side, by this property of ln, we have 4 times ln of quantity 1 plus j over 4. The left hand side of the equation is the same. Ln of 1 plus 0.046 bar divide by 2 and raise to the power 2. Next, we remove 4 from here by dividing both sides of the equation by 4, or we multiply both sides of the equation by 1/4. The left hand side we multiply by 1/4. We have 1/4 multiplied by ln of 1 plus 0.046 bar divide by 2 raised to the power 2. And similarly, the right hand side we multiply by 1/4. 1/4 multiplied by 4 times ln of quantity 1 plus j over 4. And 4 over 4 will cancel out from the right hand side because 4 divided by 4 is 1. Or we simply cancel out 4 over 4 from the right hand side. And at the left hand side we have ln quantity 1 plus j over 4. The left hand side is the same. Now j is still inside the logarithmic function. For us to have j only at the right hand side, we must start by removing ln from the right hand side. And we apply again another property of natural logarithm that says this property of ln, natural logarithm, says that e to the power ln of x simplifies to x. This is because ln, natural logarithm, is a logarithm to the base e. Thus, if you raise e to the power ln, logarithm to the base e of x, then it simplifies to x. And to apply this property of natural logarithm, we raise e to this quantity at the right hand side, and we raise e to this quantity at the left hand side. At the right hand side, we have e to the power ln of quantity 1 plus j over 4. And it is to this expression that we apply this property of natural logarithm, where your x here is quantity 1 plus j over 4. To maintain the equality, we also raise e to this quantity at the left-hand side of the equation. The left-hand side is e raised to 1/4 times ln of quantity 1 plus 0.046 bar divided by 2 raised to the power 2. And the right-hand side simplifies to 1 plus j over 4. by this property of natural logarithm, the right-hand side simplifies to 1 plus j over 4 equals the same quantity, e raised to 1/4. Now, only j must be at this side of the equation. So we remove positive 1 by subtracting 1 from both sides, or by simply transposing 1 to the right-hand side. And we take the opposite sign of 1 if we transpose 1 to the right-hand side. At the left-hand side, we have j over 4. J over 4 is equal to e raised to 1/4. And we transpose 1 to the right-hand side, it becomes minus 1. This quantity minus 1. And finally, we multiply both sides of this equation by 4, or cross multiply. Multiply 4 by this quantity at the right-hand side. And we finally get j equals j is equal to 4 times and we compute this using our calculator. If your calculator is scientific, you can compute this directly in your calculator. Or you may start with 1 plus 0.046 bar divided by 2. And when you press 0.04, you press 6 repeatedly. So we start with 1 plus 0.046 repeatedly divided by 2. We have 0.046. You press 6 many times. And divide that by 2. Divide by 2. And you should get 0.023333 is repeated many times. You add 1 to that answer in your calculator, plus 1. And the answer you raise to the power 2. Or is squared, take the square of the answer in your calculator. And we write j we have 1 plus 0.046666 divided by 2 to the power 2 is 1.0472. 1 is repeated. Now we divide ln of 1.04, by 4. We have 4 times e. We calculate ln of 1.04. 1.0472. You press 1 many times, and ln of 1.0472, 111 is 0.0461. 305,45861, and you divide that answer in your calculator by 4 because ln of 1.0472 is multiplied by 1/4 or divided by 4, and you should get 0.0115. 1/4 of ln of 1.04721111 is 0.0115 32,636 46 and 5. If you are using an expensive scientific calculator, you will get more digits in your screen, the display screen in your calculator. Now we calculate e to the power 0.011532. You have e in your calculator, e to the power 0.011. 115326 5326 3646 364654, and the answer you should get is 1.011599. Do not remove that answer. From that answer, you subtract 1. The answer in your calculator for e to the 0.0115326 364654, you subtract 1 or minus 1. And you should get 0.011599. And to that answer in your calculator, multiply that answer in your calculator by 4. And you should get 0.04. This is the answer that you should get. This is the answer for 4 times quantity e raised to 0.0115326 3645,654 minus 1. And this is still a decimal number, so multiply this by 100% and then round it off to 2 decimal places. This answer should still be in your calculator, and multiply this decimal number by 100% or by 100. and you should get 4.6. Multiplying this decimal number by 100, we get 4.639757.481%. And we round this off now to two decimal places. You count the third digit from the decimal point. 1, 2, 3. The number to be rounded up is 9. Since it is more than 5, we add 1 to the digit preceding 9, which is 3. We add 1 to 3 and we get 4.64%. This is the unknown compound interest rate compounded quarterly that we want. And this interest rate, compound interest rate of 4.64% compounded quarterly is equivalent to the given rate of 4 and 2/3% or 4.666% compounded semi-annually, which means that the accumulated value computed using this compound interest rate of 4.64% compounded quarterly for some principal P and time T is equal to the accumulated value computed at the given compound interest rate of 4 and 2/3% compounded semi-annually for the same amount of principal and for the same value of T. For your practice and assignment, please do the following exercises. Find the interest rate compounded semi-annually that is equivalent to number 1, 6.25% simple interest, 2, 10% compounded quarterly, and 3, 5 1/4% compounded monthly. For each of these three numbers, the same unknown compound interest rate compounded semi-annually is unknown. Again, for each of these three numbers, the same interest rate compounded semi-annually is unknown. So for number 1, you will find the compound interest rate compounded semi-annually that is equivalent to 6.25% simple interest. For number 2, you will find the same compound interest rate compounded semi-annually that is equivalent to 10% compounded quarterly. And for number 3, you will find the unknown compound interest rate compounded semi-annually that is equivalent to 5 1/4% compounded monthly. And for you to be able to check your answer before submission, I give you the answers. For number 1, the answer is 6.16% compounded semi-annually. This is the compound interest rate compounded semi-annually that is equivalent to 6.25% simple interest. For number 2, the answer is 10.13% compounded semi-annually. This is the compound interest rate compounded semi-annually that is equivalent to 10% compounded quarterly. And for number 3, the answer is 5.31% compounded semi-annually that is equivalent to 5 1/4% compounded monthly. And that completes our lesson for today on equivalent rates. If you have questions about the lessons today, please ask your questions in the comments below. And don't forget to subscribe to my YouTube channel, Art Kalisan, the channel of learning and leisure. Or you may ask your friends, your classmates, your neighbors, and relatives to subscribe to my YouTube channel, Art Kalisan, so they may learn as well Thank you for joining me in my class today in Mathematics of Investment.